Good evening. Tonight's guest speaker is Luna Zagorac, a postdoctoral researcher at the Perimeter Institute for Theoretical Physics in Waterloo, Ontario, Canada. Luna received her PhD from Yale University in 2022, where a dissertation focused on computer simulations and observational signatures of ultralight or fuzzy dark matter. When not thinking about things we can't see in the universe, Luna works on mapping ancient Egyptian diagonal star tables to observational astronomical data. Apart from research, she enjoys science communication and writing for astrophytes.org, playing video games and roller skating. So let's give Luna a big Mexborough and Clinton Astronomical Society welcome. Thank you.
Thank you, everybody, for inviting me and for braving what are apparently some cataclysmic events to be here, especially those of you in person. So I'll just share my screen, shall I? And ask just for a thumbs up that you're seeing slides that look vaguely correct. Great.
That's great.
Great, lovely. All right then. Well, I'm very happy to be here. Zoom even thinks that I'm happy it read my thumbs up correctly. So I'm very happy to be speaking to you today about a project that's very near and dear to my heart because it's a little bit out there, but also makes us two things that I'm really passionate about, which is on the one hand, astrophysics and astronomy, but on the other hand, heritage conservation and sort of archaeology on the very other end of what we consider sort of the sciences in this day and age. But so in any case, this talk will be based on work that I have performed and I'm still performing with Professor Sarah Simmons, who's in McMaster University, just down the road from me in Hamilton, Ontario. And Professor Simmons does hail from the British Isles, so she is a compatriot, and I cannot recommend her work online enough if you have more interest. All right, so with that, let's get started. So we are all presumably here because we like the sky and we think about the sky a lot. And to me, in my daily life as a physicist at the Perimeter Institute for Theoretical Physics, what the sky really is my window into the universe, right? So if I look into the sky, I can see things like planets and stars in our own galaxy and newly formed stars, also clouds of gas, galaxies from 13 billion years ago with these new telescopes such as JWST. And even our own black hole with really, really cool efforts such as the Horizon Telescope Consortium, and many more things. So we every day search the sky for sort of evidence of all of the rules that govern our universe as we understand it and the way that we have come to be here and if we're alone in all of these big, big questions. But on the other hand, I claim that the sky is also heritage. It is, according to UNESCO, our common and universal heritage. And it's really a fundamental and integral part of the environment perceived by humanity. And we have always observed the sky, and we have evidence of all of these different types of observatories from all over the world from very long ago, Stonehenge, for instance, being one often quoted piece. And so astronomical heritage or cultural heritage relating to the sky does recognize these relationships between humanity and the cosmos. And I really, really love this because I am something called a cosmologist. That is the type of astrophysics that I do. So that is the science that studies the origin of the development of the universe. That is why my thesis was on something called dark matter, which is all this stuff that we can't see in the universe that seems to be making and breaking galaxies with gravity that we know precious little about. But on the other way, cosmology is also the way we make sense of our place in the scheme of things. We all, in some sense, have our own cosmology, our view of how we came where we are and how we relate to the sky. And I think this intersection is quite beautiful and rich. And this is one of the things that I like to explore in my work and sort of one of the ideas that motivated this project today. So with that, let's start with a bit of a historical overview. So I will be talking to you about Egyptian star data today. Given that you are an astronomical society, you're probably more familiar with stars than with all the things the Egyptians left us, or that is at least the assumption that I will be going off of. So let's do a quick intro of what Egyptian history looks like. It's a very, very long history, starting from, 6, 7, 8 millennia ago. You can draw the line almost arbitrarily early, But I will highlight sort of three periods that we often talk about called the Old Kingdom, circa 2600 to 2100 BCE. And if you have ever seen the pyramids, if you've ever been to Egypt or just seen pictures of the pyramids, this is sort of when the pyramids are built. This is one of the biggest symbols of, say, the Old Kingdom. The Middle Kingdom, which is circa 2000 to 1600 BCE, which is maybe talked about less in popular culture, I would say, but is really this cultural flourishing of the Egyptian culture and a time where a lot of really important documents in Egyptology date from, but also sort of a golden age of the language, etc. And it was filled with pharaohs called something like Senwosret. This is one of them. I believe this is Senwosret III. And they all had these sort of big ears and tired expressions to show that they were working really hard to govern the country, which I find very cute, and also found it very relatable as a graduate student, when I too was very tired from writing my thesis. And then we also have the New Kingdom, which is often talked about, so circa 1500 to 1000 BCE. So maybe one of the most famous pharaohs of the New Kingdom is Tutankhamun, here shown by his golden mask, but also Ramses II, the pharaoh sometimes considered to be the pharaoh of the Bible, but also the great conqueror, Hatshepsut, Thutmose III, et cetera, et cetera. So this is just to give you a bit of an overview of the sort of elements we might be referencing. At the same time, it's useful to look at the geography, as geography does determine what kind of sky we see, after all. We'll get back to that. But so in terms of locations, this is sort of what Egypt looks like now, and not that different to how it looked then. So I want to just point out that here, sort of in the middle of this stretch of Nile that goes almost completely north to south, we have the Valley of the Kings, where some of the artifacts that we'll be talking about were found, near Thebes or modern-day Luxor. We also have the Abydos Temple, which is a little bit downriver, just a little bit north of the Valley of the Kings, where also some important texts that I'll reference were found, and as far north as Asyut, which is lesser known, and sort of just slightly to the north of that as well. Given this sort of basis, geographic and temporal, what kind of star data did the Egyptians have for us to sort of talk about and try to reconstruct in some way, or try to examine in some way? So we will mostly limit ourselves to the Middle Kingdom and the New Kingdom. I've drawn an arrow of time here, just approximately. It is not to scale, so don't worry about exact dates or anything like that, but just to give you an idea. So I will mention three types of data. One are the diagonal star tables, which were mentioned in my introduction, which I should really change because they work on a slightly different element now, but we'll get there. So these are star tables that look just like this. They are found on non-royal coffins, so coffins not belonging to the royal family, but maybe to some of the sort of higher levels of society, mostly from Asyut. So that's that northernmost point that I showed you, circa 2000 BC, or they date to circa 2000 BCE. And the last version that we find later is on the ceiling of a temple called the Osirian. That is in Abydos, the middle point of the 3 points that I showed you, circa 1200 BCE. Then we have something that is sometimes called the Transit Star Clock, or the Book of Nut. That is also found close to the version of this diagonal star table on the Osirian ceiling, dating to circa 1200 BCE. So again, that is that middle point. And then the latest type that I will be introducing that we have are Ramesside Star Clocks, which we will talk about the most today. And they are found in the Valley of the Kings in royal terms, circa 1150 BCE. So slightly later than some of these other elements. And the reason that I will be focusing on Ramesside Star Clocks today is that a lot of work has been done on the first two types that are sort of linked together in a way that I'll explain in a moment. But it does seem likely that they show some type of idealized sky, maybe used more for religious purposes or funerary purposes than, say, an observation of the night sky as it is. Whereas we do have a suggestion that the Ramesside star clocks might be purely observational, so purely recordings of something that they saw in the night sky. And so for that reason, I like to start with the last one first. Now, with that in mind, the diagonal star tables, so they look a little bit something like this. This is a detail from one of these star charts on the coffin of Idi in Asyut. So they are found mainly on coffin lids, except for that one example that is found in a later temple. They're mostly from the Middle Kingdom. They're mostly from Asyut, so this particular necropolis during this particular area of Egyptian history. A few from Gebelin, Thebes, or Luxor, and Aswan, where Gebelin and Thebes are somewhat close, and Aswan is all the way to the south, but really the majority is from Asyut. They're divided into two types called K tables and T tables based on what the first star to appear is called. We call the sum total of stars decans occasionally. They're a set of stars or asterisms that are very authentically Egyptian in the sense that they keep showing up in later historical corpora. Even after sort of Greco-Babylonian ideas of the zodiac have taken over, but seem to lose some of their function, perhaps. And there probably is an observational basis, but it does also seem fairly idealized in the sense that it's hard to take this behavior and put it on the night sky as we understand it and reconstruct something that really makes sense and really tracks stars. So to give you a quick overview of how they work, this is a drawing from Neugebauer and Parker, who have these 3 volumes of Egyptian astronomical texts published around 1960 that are excellent and the source for a lot of these investigations. So what I really love, and this is half of a coffin that I'm showing you just to be a little bit brief. What I love about these is that I look at them and what I see is ancient spreadsheets. What I love is that apparently as people, we have always had the need to organize data into spreadsheets, including stellar data. And I find that sort of like very human and nice. So what we have here are 12 rows, which are thought to represent the hours of the night. The ancient Egyptians always had 12 hours of the night, regardless of the time of year, which essentially implies that the length of an hour is variable, because if you divide the night into 12 equal parts in July, you will probably get a very different number than if you divide it into 12 equal parts in December. So an hour was a 12th of a night rather than something that was 60 minutes long or 40 minutes long or any preset amount of time. On the other hand, what the columns show here are weeks, and we go up to week 17. If we showed the other part of the star table, we would go all the way to week 36. In ancient Egypt, a week was 10 days, 36 times 10, 360 days, plus 5 days at the end of the year, which weren't organized into weeks or months. They were known as epagomenal days or days upon the year. And so those were the days where maybe in modern parlance, let's say the veil between this world and the other world was thin, and there might be demons and stuff about. And so the way that you protected yourself against all that bad juju is you got drunk and partied for 5 days, which I think is a tradition that we should bring back, quite frankly. But in any case, so this is a coffin belonging to a woman named Ashit, which we know because that is her name right there, written in hieroglyphs. And what this essentially does is along with the actual data presented in the grid lines, there is the central text that says that the coffin belongs to Ashit, and also it presents certain constellations on this vertical line that aren't part of the data, and the constellations that are invoked are called Sopdet, which we have reason to believe is Sirius, Sak, which we have reason to believe is related to Orion, the foreleg, which maybe by just looking at it, you can guess what it is. This is the Big Dipper, and my personal favorite. And then it evokes a goddess Nut, which represents the entire sky. And the reason these are called diagonal star tables, digging into the data now, is because the stars do indeed move diagonally. So if you can see my pointer, and if you can't see, I'll try to be specific just in case. So in week 1, you can see in hour 10 that there is a star drawn saying that we are recording some star or some asterism, let's say. And there is a hieroglyphic inscription that gives this star a name. And the name is something like he who is in the boat, right? So it defines the star, but it's not necessarily a name that I associate with a particular bright spot in the sky. So we can see that in week 1, it is in hour 10. In week 2, it is in hour 9. In week 3, it is in hour 8, et cetera, including when it crosses the middle passage. And so that's what these stars do. They sort of drift diagonally across the table and are presumed to be an idealized version of some sort of timekeeping device. So that is the earliest sort of spreadsheet-like data of some stellar observations from ancient Egypt that I am aware of, or certainly that I will be talking about today. The next one, which I called the Book of Newt, is related to these in a sense because it appears alongside the latest version of these in a temple called the Osirion in Abydos, circa 2000 BCE. And it references Newt because Newt was the sky goddess. And so, however, this is the name that we gave it sort of in modern parlance. Its original title is called The Fundamentals of the Course of Stars, which was translated as such by Alexandra von Lieven in 2010. It has founded this incredibly important Osirion temple at Abydos, circa 1200 BC. I misspoke earlier, and several other iterations, but the one at Abydos is the one that is generally referenced. It discusses various astronomical phenomena, including the movements of the decans. So the decans are all of those stars that were mentioned in the diagonal star tables. And so clearly these are related texts because they refer to the same set of stars. And it seems likely that this is based on some progenitor text that dates way earlier, say to the Middle Kingdoms, closer to those earliest star clocks. But the earliest version we have here is from Abydos. And it also has a very important religious text linking sunrise and rebirth. So it is sort of, on the one hand, almost a handbook or sort of an additional inscription describing the diagonal star clocks and the origins of the decans, but at the same time, it is a religious text with some religious implications, especially when it comes to, say, the pharaoh's journey and the afterlife, etc. So it does both things here. And it looks a little bit something like this. So there is a lot of text, but also there is a drawing. And what we see here is the body of Nut, the sky goddess. She is stretching over the earth as she was often shown, so that her body is indeed the night sky. And the person holding her up is the god of the air, Shu. So, the night sky is up here. There is some atmosphere, there is air. And if you saw, you might see different versions of this where her husband, the earth god, is also lying down. So the earth, the air, and above it, the sky seems like a very reasonable cosmology to start from. And so there are two parts. The part one, which is sort of listed around her hands and by her legs and feet, describes the topography of the sky as the ancient Egyptian saw it, the daily course of the sun, and the actions of the sun god and the deities, but also references the actions of the decans. Whereas the middle text is more of a dramatic text, so this is what I'm saying in terms of it has this religious significance, and it is an argument between the god of the earth and the goddess of the sky, and the argument is that she keeps eating her children, but gives birth to them later, which is assumed to be sort of the effect of stars disappearing and not being seen in the night sky for some number of days before rising again. So there's a lot of metaphor here within the information. And so this is why the Book of Newt, or the Fundamentals of the Course of Stars, is often associated with the diagonal star clocks. However, and so the thing that it says about the decans in terms of being a handbook for what they do, they perform certain actions, and the actions are unfortunately a little bit mysterious. So it does take, it is kind of hard to interpret them in terms of wanting to put them in an astronomical context and create a model of stars that move and can reproduce these data. So the decans do several things. They are first, before spending 90 days in the west. They spend 70 days enclosed by the duat, or the underworld, before they are born. Then they spend 80 days in the east and 120 days working. So the way that this has been sort of interpreted is that the 70 days enclosed by the duat, which is the underworld in ancient Egypt, is the time that Nut has eaten them, so they are not visible in the night sky at all. And then when they're born, they heliacally rise. They are seen for the first time after 70 days. They spend time mostly in the east. We see them rising. For 120 days, they are working. And working is assumed to be marking an hour for 12 weeks, or 1 hour for 10 weeks, pardon me, because there are 12 hours of the night and the 10 weeks that they are working before they are first, and then spend 90 days in the western part of the sky and aren't working, meaning they aren't being used to tell time. So this seems like a very reasonable thing to suppose, but putting this in, say, a planetarium software and trying to recreate this in a way that makes sense, say with Sirius and Orion, which are or some of the stars of Orion, which are the mentioned constellations, does prove to be a little bit tricky. It doesn't quite work as cleanly as we would like it. But nevertheless, these are very interesting texts. And so finally, let's talk about Ramesside Star Clocks, which will be what I'm focusing on today, because that is what my recent work is based on. They are quite different than the previous ones. So they are found in a royal context. So they are found in tombs in the Valley of the King. There are 4 instances of them, so 4 versions that we have in KV1, which belongs to Ramses VII, KV6, which belongs to Ramses IX, and KV9, which is shared between Ramses V and the Sixth, because during this time, the kings were all, as you can see, they were all named Ramses. They all really wanted to be as great as Ramses II, but their reigns were getting shorter and Egypt was getting a little bit more unstable. So it wasn't maybe the happiest time for kingship, let's say, as evidenced by the fact that 2 of them ultimately had to share a tomb. What we have is 24 tables, like the one pictured on the left. And each spans 15 days. So 24 times 15, we again have 360 days, or the length of the Egyptian year, minus the 5 days upon the year described. We also, the epigomenal days aren't mentioned. Maybe they're implicitly included in the last table, but probably not. And the present, one of the things that suggests a more sort of observational origin here is the presence of this human figure, which seems to be either the observer or either like a friend or a statue that the observer was observing with respect to, which I will clarify in a moment. But in any case, because these seem a little bit more casual, a little bit more imperfect, a little bit more possibly observational, it's a really great start to reconstructing the timekeeping model behind the data, which is ultimately what I'm interested in doing. Basically saying, how did the ancient Egyptians observe the night sky and write down this data in a way that yielded this text? How did they relate to the night sky? And so here is a more detailed drawing. So this is from Lepsius, the German title, which I will not attempt to pronounce. But basically, this is from a Prussian expedition back when Prussia existed. And so we have, which is very good because a lot of these texts are now very damaged. So we have these drawings that we can read the hieroglyphs off of and have and can reproduce to look at the data within. So a few things to notice here. There are lines of text on the right here, which tell us the names of these asterisms or stars and also the day and the month. So the first line here says day 1 of the month of Achet, and then names whatever this star is. And it says beginning of the night. The next one says end of the first hour. The next one end of the second hour, et cetera, et cetera. So for that reason, we note these rows as 0 to 12 because 0 tells us the start of the night, or if the first one tells us the end of the first hour of the night. So once again, we have sort of 12 hours, I guess 13 rows, but really indicating 12 hours. And we have these positions that are given in the columns, which we call the central position 0, and then plus or minus 1, plus or minus 2, or plus or minus 3. The positions are also reiterated in the text, and they generally match where the star is put, unless they were sort of running out of room and had to put it down somewhere, which happens because scribes were copying these things from some central papyrus or something like that, and human mistakes happened, as they always have. But all of the positions are given with respect to this human figure. That's what I mean by saying that it was probably like a statue or a partner that was accompanying the observer. So the central position, which we call 0, is really called opposite the heart or upon the heart. Then the +1 or -1 positions are given with respect to the left or the right eye, the -2 or +2 with respect to the left and right ear, and then finally -3 and +3 with respect to the right and left shoulder. This is a little bit complicated by the fact that the words for left, right, and east, west are the same or indistinguishable in hieroglyphs. So it's either the west and the east eye or the left and the right eye, let's say. But in any case, they're given with respect to the human figure. So this does imply sort of a human observer in some sense. Okay, so that was sort of an overview of the types of astronomical data we have in ancient Egypt, with an emphasis on the Ramesside star clocks, which we will be getting back to. But the way that I contribute to this effort, I am not an Egyptologist. That's not what my PhD is in. I have a background in it, but not that level, like, for instance, Professor Simmons. So where I come in is with sort of my astronomer's urge to include Python into analyzing everything. So it's sort of adding the digital humanities bent to this hieroglyphic data, which I think is very fun. But in essence, what do we have when we boil it all down? Once upon a time, there was some Egyptian observer, which I'm just representing with the C described here, that performed some observations of the night sky as it looked back then. So say circa 1300 BCE, when these things first appear. And through some method of choosing and writing down stars, they wrote astronomical records, for instance, the Ramesside Star Clocks. And so given these astronomical records, and given that we know the contemporary positions of stars, right? We know what the sky looks like now. Can we reconstruct and test this method behind the observations? So as an astronomer, I want to know how they were observing. And so our first priority is not to match individual stars to the stars that we see, like their names and our names, but rather to really go after the method. And hopefully this can be complementary with some of these other people that have looked into trying to match star names. And so what we need is a model. And every time that I make a model, which is often because that's kind of in everything that I do in my daily life, I like to remember the statistician George Box, who said that all models are wrong, but some models are useful, right? And so the question is, how do we make a useful model that is a simplified version of what they surely did, but that can help us say something new or something interesting? So first, we have to review the primary source material, right? It has to be based on what we know about them, which is sort of what we just did. Then we collate and discuss the relevant factors that could impact observations. Like if I'm an astronomer, what is going to change what part of the sky I'm looking at or how I am looking at it? And then plan future testing of its model and its parameters with Python. And so this is also kind of the outline of this talk, where we've also already done the first bit here. And so the first bit is to wind time back, right? They certainly weren't observing the sky in 2025 AD. We know that it was quite a bit ago, and we also know that the sky looked differently then. And the reason the sky looked differently is because of the precession of the equinoxes. So our Earth wobbles, as shown in this GIF by Stephen McIntosh. And basically what that means is that celestial north moves on this curve that is vaguely marked by Polaris, Deneb, Vega, and Alpha Draconis. So we actually live in kind of a special time to have Polaris as our North Star. That's really kind of special for us, I think. But back then they wouldn't have, because if you wind the clock back 3,000 years, 4,000 years, there would have been no North Star. This arrow would have been pointing somewhere else. And so there are works that have calculated how to do that and put it into, for instance, Python. We can also calibrate it with planetarium software, such as Stellarium, which anybody can download and use. So we can, do some reasonableness checks and see how this all would have looked like. And we can use the coordinate system that observers like to use, which is sort of azimuth and altitude, because they are based on where the observer is standing. They're sort of human-centric rather than sky-centric, if that makes sense. And so all of this can be done with a code that I made called the CanoPy, which also functions based on something called AstroPy, which is a wonderful, wonderful module that astronomers today use to point their telescopes at the correct things and gate data and calculate things. So I had a lot of fun just updating this to be looking at a very old sky rather than the modern sky. And moreover, we can go a step further. If I tell the CanoPy some form of model for how these ancient Egyptians were observing the night sky and creating these Ramesside star clocks, I can start to create synthetic Ramesside star clocks and see how well they match the original data. So, right, we have this data, right? We have their data, and we have the ability to precisely model the sky and wind that clock back. So then the missing component is this method that we were after. How did we generate the data set that fills in the system? What is their observational technique? And so this isn't a simple problem, and there are many interacting factors to consider before even building a model. And so this is what Professor Simmons and I did in this work that we submitted to the Journal for the History of Astronomy earlier this year. We enumerated all of these factors as we saw them, and we basically divided them into factors that we can reasonably assume. Where were they observing from? Probably Luxor, because that's where this data was found, but also it is sort of in the middle of that north-south spread of Egypt. So even if they were observing slightly from the north or the south, well, the horizon would have looked a little bit different. We're sort of making the least possible error. When did they make it? well, let's assume circa 1300 BCE, though of course we can amend that later. We assume that it had good weather, good horizons, stuff like that. There are factors that we can test. So this is really digging into how they did their observations, which we will go into in a second. And then finally, there will be some human factors that we really cannot know even in principle. We can't know how diligent they were. We can't know how tired they were. We can't really know how tall or short their observer friend was, if they were observing with respect to somebody, things like that. And so these are things that we can safely put to the side because we simply can't address them scientifically. So what parameters can we test then? Well, looking at the data as it's supposed to come out, one first question is how wide is this horizon, right? What is the distance in the sky between a star that is above the left shoulder and a star that is above the right shoulder? And if I'm imagining that I'm looking at somebody that is standing in front of me and looking at the stars, say, rising, setting, transiting, I don't know, performing some action above each of their shoulders. This will depend on how close or far I am from them. This will depend on how wide or narrow their shoulders are, et cetera, et cetera. But in any case, we can subsume all of that in how wide is this horizon they are observing. We can also ask, what is the central position point? So what direction am I looking at? Am I looking due east and watching stars rise? Am I looking due west and watching stars set? Am I looking south and watching stars transit, et cetera? We can also ask if there are gaps between these bins. So there are 7 allowed positions or bins, but you'll note that the stars aren't in between 2 lines. They're not in a cell as we would imagine it in a modern spreadsheet software. They are on the line itself. So does that assume some very fine level of precision? And are there gaps in between where even if a star is there, it's too far from the exact position above the shoulder? That is something that we can also guess and check. How high do we want to look in the sky and and still have the star be useful? So for instance, if stars are rising or setting, meaning if I'm looking east or west, I probably want to be looking closest to the horizon. But if the stars are transiting and I'm looking south, I can look almost arbitrarily high up. How high is too high where they're no longer useful? And again, there are just human choices. So if there is more than one star that is a candidate, do I choose the brightest star? Do I choose the star that I like the best because it has some religious significance to me or to my way of thinking? Do I choose the star that is centered, if that is an option, since we do see that the center position is favored? Are there other ways that I choose star as a human making a choice? So these are some things that we can implement into our choice algorithm, but ultimately we can't know with great precision. And the idea for verifying this is to create these synthetic Ramesside star clocks, or if you like, fake Ramesside star clocks, and compare statistically with the total set of the real data that we have. So in this way, we can test our observational model and to some extent human choice. So for instance, a relatively simple but a very useful heuristic is to ask, how many observations are attested per position bin? So of all of the stars that appear in all 13 rows of all 24 tables, what is their spread? And if we calculate that for the real data here, you can see that the central position is indeed very preferred. The eyes are sort of the next down. Then the ears, though there seems to be a preference for the positive numbers, but then the shoulders seem slightly more preferred than the ears. That's kind of interesting. So if we are trying to statistically match our guesses of the observational model and their yielded synthetic star clocks to the real thing, this is how we can try to narrow down the possibilities and try to get at what they were doing. And yeah, these are the 2 observables that I just talked about, the sort of preference for the central bin and the fact that the ears seem less preferred than the shoulders rather than just falling down monotonically. Right, and so a very reasonable way to do this is to look at the real sky as we see it today, wind the clock back and see what's happening. That's certainly what they would have been observing, and that is certainly a step that we will do. But also real stars are messy, and we all have something attached to them in the sense that we have this sense that like, oh, they knew about Sirius, so probably one of these is Sirius, or oh, they knew about some of Orion, so probably some of it is in Orion. Which part of Orion? Well, probably the belt because we like the belt, but did they like the belt? There is sort of cultural significance to the real sky. And so we thought about making 2 types of, let's say, fake skies. So for instance, this is just more of an example for talks than a real data set. What if we just had a sky full of Siriuses, right? What if we just changed the right angle, the right ascension of Sirius and just populated one big band of Siriuses across the sky? If they did indeed like Sirius, if it was an important star, maybe it was in some sense the best star because it's a really bright star and it's a really religiously significant star. Would that have been good for them? Does that help recreate their model in some way? Like, are they looking for stars that look like Sirius or that act like Sirius in some sense? But really, the one that I'm more interested in is what if we made a totally random star field? So what if we just simulated some stars that have the same statistics as our real sky in the sense of the number of stars, in the sense of the distribution of their brightnesses, in the sense of the distribution of their RA and DEC, and run those through the model. And the idea here is that this contains all the same statistics as the real sky, but not the element of human choice. And so if there are some things that we can only reproduce on the real sky, making human choices, but not on the random sky, then it's likely that some human preferential elements came in there. And so just as an example, this is what that might look like if we were to construct a synthetic or a modern, if you like, Ramesside Star Clock on that Sirius-only data. So real Sirius here is marked as S00, and I've presented two tables that are produced by my code. So on the left is January 1st through 15th, and on the right is July 1st through 15th, 1300 BCE, and we are looking due south. And so what you can immediately see, for instance, is that these don't work, right? These don't even kind of look like the real data, and not just because they're done in Excel. They don't look like the real data because they don't have that preference for the central bin. In fact, these look kind of weird. You can see that there's multiple choices, so you would still have to make a choice, but there's almost nothing in the central bin in January. And then in July, they're spread as well as you like. However, if you just chose all of these that have an object in the central bin for the central bin, it's still not showing the same level of preference as before. So this is the algorithm that we are sort of implementing to look for creating mock data, if you like, similar to how modern astronomers make mock catalogs to test some of their computational pipelines before using them on data from telescopes such as, say, the Rubin Observatory and stuff like that, and compare them statistically to the real data to see what happens. And finally, also, if you, given that these are only two tables, of course, it could be that something more interesting is hiding in the other tables. But if you do the same sort of histogram, you see that the spread of Sirius is sometimes even. So no surprise, the completely contrived version where all of the sky is filled with Siriuses doesn't quite work. And so to wrap that up, let me summarize. So the exact observational model for generating the synthetic Ramesside star clocks is still unknown, but digital open source tools like DecanoPy can really help us elucidate these possibilities, and making these fake or really synthetic Ramesside star clocks is a promising direction in doing this statistical matching. I think is a very modern astronomer way to approach this really ancient problem, which I find exciting. I like those kinds of mixes. And so ultimately, the goal might be to map more Egyptian names of the stars and asterisms to our sky. But before that, what I really want to know is the observational model that they were using. It all goes towards how they are relating to the night sky. And finally, I think this is probably not news or not surprising or exciting to this group of people. But I said earlier that I see the sky also as human heritage, as does UNESCO, but I also see it as heritage in danger. So I'm not talking here specifically about, again, something like Stonehenge, like sort of the physical remnants of ancient cultures and how they observe the sky or the sites where they observe the sky. I'm talking about light pollution. And I simply think that access somewhere close by to an unpolluted night sky is an inalienable right of humankind. We're all astronomer lovers here. And so I think that's a right that we should all have. And so just a quick shout out to some of these wonderful organizations doing this work around the world. And finally, I will once again say that if you are interested in Egyptian astronomy or want to hear more about any of these things that I've sort of glanced over, Professor Sarah Simmons has some really excellent talks online. This is one that's on YouTube, but if you Google her in general, I believe there are others, and I highly, highly recommend. If you're fast enough, you can snap a picture of this QR code, but otherwise, if you Google her name, they should be easy enough to find. And so finally, with that, I'm really I'll thank you for inviting me and for your attention today. I'll invite any questions and just leave some of the references that I've referenced today. And if you don't get to ask a question today, you can find me through my website. So yeah, thank you again.
Luna, thank you very much for a most enjoyable talk and a real eye-opener. The first thing that struck me is that I'm not too sure human beings have developed that much, just that their technology has got better over the last 3,000 years. And that's about it. Could I ask you to stop sharing your screen? And
absolutely.
We can go back to gallery view and look at everybody. And once again, thank you very much for a most enjoyable talk. Questions and answers online, if you can put up a digital hand. In the room, attract my attention somehow, and we'll bring you into the conversation. So, Graham, in the room.
Is there any historical knowledge that the ancient Egyptians actually needed to tell the time during the night? Obviously, in medieval England, they needed to tell the time at night to sort out their monastic offices, but is there any reason to suspect that the Egyptians wanted a way of telling the time at night?
Yeah, that's a very good question. And actually, there is something called the Karnak clepsydra or water clock that I encourage you just to Google if you want. But so they did have this technology, which is essentially a water clock. So it's sort of a purposely shaped bowl that you fill with water, and it sort of leaks out at certain levels. And by checking the level of the water, you know what time of night it is. And indeed, these hours are not equal length hours. So this supports the idea that you're dividing the night into 12 at different times of the year, rather than sticking to, oh, an hour must be 60 minutes. So there is evidence that they were telling time for sure. Linking that to stellar, using stars for timekeeping is, I think, more interesting, given that, you know, they are listed as the hours in this text, for instance. I think it's likely that they were marking hours, but that begs the question, why is this in royal tombs? Was this actually used for thousands of years by people? And then, you know, Ramses IX was like, oh, actually, I like that, slap it on. Or what? Because you might imagine something really hoity-toity, like these are the hours of the night that certain rituals have to be performed by the priest or the pharaoh to make the gods happy and make his time, you know, in the afterlife grand. Or you can imagine that they were used to, you know, like meet your friend down the pub at the proper time. So I think it's quite curious that they appear out of nowhere, are really popular for the short period of time, and then disappear again. So yes, we have evidence that they certainly told time with this other technology, for instance, the water clock, off the top of my head. What the role of stars in telling the time, that is sort of still what we're investigating. But I think just from the text of marking beginning of the night, end of first hour, end of second hour, it seems likely.
Okay, great. Can I just add to the answer in that ancient civilizations in the Eastern Mediterranean, they did a lot of commerce at night, and so they followed the lunar cycle. So on a full moon, you might have a street market that ran for a lot of the night. There was a lot of nighttime activity. So telling the time at night would be.
In countries with Ramadan, they did most of their work at night because they were fasting in the day.
Yeah. So well, that would have been after 600 CE, but yeah, before then, the Jewish people sort of for the fortnight around full moon, they had a very busy evenings and early mornings. So there's that. I'm looking around for questions. Roy Gunson in the room.
It's more a comment on that. It's very interesting to see these ancient pictures and writings that enable you to actually see how they thought. One of the things that I was going to sort of mention is there's I believe there's an Egyptian tomb, Zenonut's tomb. It's actually pictorial and puts the 4 planets rising: Mercury, Venus, Jupiter, and Saturn, I think it is. And Mars is in a boat sinking in the. I think that through that pictorial reference, they think that's actually the exact time this guy died. I think
Yeah.
1536 BC. They've got it like 5th of May at 4 AM. I think that's just.
Yeah, no, absolutely. They knew about the inner planets, that's for sure. We see them depicted. The Dendera zodiac, for instance, which is now in the Louvre, is a famous example. And when some of these pictures are seen with a bit more sort of historical context, let's say, sometimes it can really help narrow down the time period because you know what positions the planets have to be in, and so you can sort of wind time back.
I don't really want to put you on the spot, but from the models you've run and the work you've done so far, in all 3 of the systems, there was obviously a reference direction. Have you any idea what the reference direction is likely to be?
Reference direction in terms of direction of observation, like where am I looking? Yes. So Neugebauer and Parker, who are the 2 mathematicians and historians that wrote these Egyptian astronomical texts, which are very useful books and very hard to hunt down because there's not many of them in print. So we're all exchanging PDFs at this point. I believe for both, they state that the obvious thing to do is look due south, because then you're looking at the southern meridian, you are seeing the stars transit, they are moving, sort of like directly across the sky. It's easier to get equal hours that way, et cetera, et cetera. And that's not a bad assumption. However, I'm not satisfied that it has been tested beyond the level of an assumption. So I think it's not unlikely that it's due south. That will certainly be the first test that I will run. Actually, Sarah and I met just yesterday, and we're outlining sort of what examples to test with the code, and sort of when we'll next meet to dig through some of them. So I would not be at all surprised to hear that it's sort of southish, especially since if you're looking a little bit higher up from the horizon, it's hard to it's not as obvious as a star rising to see it transiting, but you're not looking like at the horizon. You don't have issues with atmosphere. You don't have like a mountain in the way or something like that. But on the other hand, we are assuming that they knew what the southern meridian was, and that seems to be a very modern thing being imposed on a culture that may very well have known about it, but we don't exactly have evidence. So I don't know if that is the correct answer, but that is certainly the first thing that I'm looking forward to testing.
Why would you say that they wouldn't know what the southern meridian or where the southern meridian would be?
They might. They very well might, but it's not obvious to me that they would. I think part of the trickiness here is that we also have such a relationship with the sky that it's often very tricky not to impose modern or even just simply Greco-Roman, because that is sort of where constellations come from, ideas. And so I'm not saying that they didn't, but I'm saying that there's nothing in the text that tells me that they definitively did.
Is there nothing in the text that says that it could work out where the southern meridian was from the observations of the sun during the day?
So there's nothing in the text that tells me that specifically. It's of course very possible. They did very precise calculations in terms of building alignments, etc. So clearly they knew how to find the cardinal directions very well. Whether they thought to project that as a line on the sky is more of a question. But it's very possible. It's plausible that there was a roof of a temple when you did your observing, and you put a little X on the ground or a circle on the ground where you stand, and you had like a little statue, let's say, of a seated dude, or just like or even just a stick, like attached. And if you stand on the circle and look at the stick, that's the southern meridian, and that's fine. It's possible, but I don't know that it's true. So it's certainly something that I would like to investigate. but I'm not taking it for granted, if that makes sense.
It certainly does. Tony,
Just picking up on that point, when you were talking about, in your early slides, you were talking about the stars rising and disappearing. The times of rising, the time period rising and the time period of disappearing wasn't symmetrical. So does that hint that the southern meridian was not at the meridian, what we would call the meridian, because it's not symmetrical? If we observe the meridian, it will be symmetrical. Those numbers weren't.
Yeah, no, I agree. So I don't think that it's completely due south. I wouldn't be surprised to hear that it's southish. But that is, for instance, one of the problems with the diagonal star clocks, because one sees, for instance, Sirius and says, okay, let's start with Sirius at the latitude of about 30 degrees above the equator, which is where Luxor is, where sort of like the middle of Egypt is. How long is Sirius not visible for over the course of a year, like at all at night? And one gets something like 67-ish days, depending on how one defines visible, because it might rise slightly above the horizon, but not be visible because of atmospheric effects or horizons or something like that. And so it's like, cool, that works. So then let's say that that is what happens with Sirius, and then let's try to find the other stars that do that. And that's where we run into some issues. That's where that asymmetry comes in. And I think part of the issue is that it is kind of hard to stars don't move as neatly as we would like them to. One has to think on this great sphere, which is not what we're used to thinking on in daily life. And so doing all of these calculations by hand in 1960, if you're Neugebauer and Parker, is quite onerous. But me making Python do those calculations for me is relatively easy. So in terms of people never changing, but our technology progressing, I think this is one example of that, where it's a good starting point, but now we have a little bit more of the technology to dig into it in a way that's not very mathematically onerous. But I agree, that is one of the sticking points in terms of say these diagonal star clocks, and whether they're a real sky or an idealized sky where every star sort of behaves like Sirius.
Okay, well, another question, if I may.
Yeah.
You were referencing back to stellarium. So
Mhm.
how to reference the stellarium clock to the epoch that you're trying to match your data to?
So stellarium, we can wind back sort of arbitrarily. It has some presets for Egyptian constellations and data, which I'm not quite confident in. But it is one way simply to make sure that my algorithm is calculating the positions correctly, or at least in line with stellarium. So we use it as sort of a cross-check and an additional visualization tool. Was that your question, or did I misunderstand?
No, that's fine. I just wanted to know the different, because we have trouble with our own calendars as we go back, because our calendars change.
Yes. Yeah.
Yeah, I think everybody putting on their stellarium tonight, winding it back, seeing what is the whole star at that point.
I'm using case.
Oh, fair enough.
So there is something in my code called a stellarium offset, which is they're winding stellarium back at some point. We do our times in JD and Julian dates, because that's useful in a continuous way of marking time. So computers love it, astronomers love it, and I'm an astronomer who programs computers, so that works for me. And there is this jump at one point in stellarium, which I'm not quite sure why it happens. So to match stellarium, there is this offset. I want to say 15 days or so in JD. That is sort of toggleable on or off in the code. So yes, winding stellarium back beyond a certain date, there are certain details that one has to be aware of. It wasn't as straightforward as I thought.
Gary Kite, online. Gary, can you turn your microphone on, please?
Yep. Okay.
And your question, please.
Yes. Great talk, by the way. Absolutely fascinating. Thank you. I've had the good fortune to visit a number of tombs in Egypt, and you mentioned the Zodiac at Dendera. and the astrological aspects of that.
Mhm.
I've also had the good fortune to visit some Maya temples and some Maya areas. And I was just wondering, is there any correlation between any observations that the Mayans have made of the night sky and the Egyptians, or have we not delved into that aspect so much with the Mayans?
I have not delved into that personally. I know people have worked on Mayan archaeoastronomy a fair bit. So, for instance, I first got into these questions in uni, where I was taught by Professor Anthony Avini, who wrote a lot of books, for instance, specifically on the Maya, the Aztecs, and the Incas, but I think with a real emphasis on Maya. So from those uni courses and from my work, I didn't notice a sort of through line immediately. But I don't know if somebody has looked at that sort of in a more systematic and efficient way.
Thank you. Thank you.
Thank you.
Okay, and I'm going to take one last question from inside the room. Back to Graham, please.
The business of the eye, ear, shoulder, etc., presumably is some sort of unit angular measurement. And your assumption seems to be that you're sighting along an actual live physical person, who is standing in front of the astronomer. But another method that occurs to me to get a standardized angular measurement would be if there was a widely distributed effigy of a human figure, which would be appropriate in weight and size to hold at arm's length. I'm thinking of the earliest attempts to measure angles at sea in the Middle Ages, that you had a cross staff that you held at arm's length. And so could the angular measurement be a physical measurement, a linear measurement of some standardized object that would be standardized by holding it at arm's length?
Yeah, that's quite possible. Yeah, who the human figure is and what it's doing is somewhat mysterious. There's sort of just amongst the Egyptologists, there's some discussion of this, because if you remember what he looks like, it's a man in sort of a relatively simple kilt, shown with no hair, but with a beard. And generally, the only person shown with that kind of beard is Pharaoh, but there's no other pharaonic regalia that he is holding. So is he Pharaoh? Is he a priest? Is he just some dude who likes a beard? Unclear. But also, yes, whether it's a representation of a literal person or a statue or yeah, like you said, just an effigy that I hold at arm's length. Sort of what we are trying to do on the strength of our model is to say that in some sense, I don't care how they measured the angular distance. I'm just trying to get the angular distance in terms of sort of projected azimuth that can reproduce the data as well as possible, and then from then I can backtrack some theory on what that makes sense to be, whether it makes more sense to be a statue or an effigy or what have you. But ultimately, that's kind of a thing that I can't fully know unless something new is found in the archaeological record. So that's what I mean by sort of like abstracting these things into sort of a wrong but useful model. It doesn't tell me all of the things, but hopefully it tells me something. And there was always the possibility they were looking into a body of water and that they were looking at their own reflection and what's directly above. That is also something that has been suggested over time. So many possibilities.
Okay, I did say that was going to be the last question, but Ed Bottomley is one of these people who always comes in right. Ed, can you undo your microphone, or do your microphone and carry out your question? And this will be the last one. Okay, Ed, over to you.
Thank you, Paul. Lovely talk. This shoulder, ear, eye, isn't it not just an ordering?
In what sense?
It's just an order. It goes from, say, left to right. So the
yes.
shoulder, ear, eye, heart, eye, ear, shoulder. It's just an ordering. And when we looked at the cells you were showing us with this central cell, it looked to me as though if you were to assume looking south and you had 180-degree vision, each one of those cells would be 30 degrees. And it all seemed to match up quite nicely to that. But that, again, that's a 21st century view being imposed on a But we're talking about a real physical person. I would just assumed it was a metaphorical person, and it was just to give you an ordering, and it wasn't a real person there.
Right. So again, that's absolutely possible. It could absolutely be a metaphorical person, but in any case, I need to have 7 positions that I have in some way defined on the horizon that I'm doing my observations with respect to. And so I haven't tested all the way to 180. I was assuming that it was something sort of like within a more narrow human field of view. But that's an interesting thing to try. I think it gets a little bit more complicated once we get down into the weeds of matching some of the other sort of like statistics or observables, if you like, of the data in terms of how many individual stars appear all throughout, 47, for instance. But also we never see we see stars skipping certain tables. We never see them moving back. So it is sort of like a narrowing down, if you will, of what we need the stars to do or not do in order to recreate the data set as we have it. But that's interesting. That is certainly something to try with a very wide field of view, because ultimately it doesn't matter if it's 7 sticks I stuck into the ground and called them a heart, eye, shoulder, whatever, or if it's an effigy I'm holding, or if it is an actual person. These sort of, if I knew which one it was, they would maybe suggest a width of a horizon. But again, if if it is, let's say, a person who is at the position of my camera and I'm standing back here, I am seeing a much narrower horizon than if I stand here and look against their head and shoulders. So in some sense, this is absolutely interesting. I would love to know what it actually is. But I think this is where we need archaeological record. In our case, what we really care about is how wide is that horizon and how those positions are divided. And yeah, I guess there's nothing saying that it couldn't have been 180 degrees. That's definitely something to check.
Okay, all right, Ed.
Yes, brilliant. Thank you.
Ladies and gentlemen, will you join with me in giving Luna Zagorac a huge Max Bretton Swinton Astronomical Society thank you for a wonderful talk. Thank you very much, Luna.
Thank you very much for having me. And thank you for all the excellent questions.